Today we're going to be looking at section 3.3, measures of relative standing, and also box plots. Okay, in this section we're going to be looking, like I said, at measures of relative standing, which are different ways that numbers you can show the location of data values relative to other values within the same data set. So we'll be looking at percentiles and quartiles and also z-scores and some of these other things that give us some measure of relative standing. The most important concept would definitely be the z-scores, which we will be using going forward in other chapters as well. So it's really important that you understand what a z-score is. Like I said, we'll also talk about percentiles, quartiles, and also the statistical graph called a box plot. Okay, the first one that I want to mention is a z-score. A z-score is a standard score. So it's really important to understand that a z-score is just taking a data value and standardizing it. So you standardize it to this standard score, and it actually represents the number of standard deviations that a given value is either above or below the mean. It's going to be a positive z-score if the data value is above the mean, and it's going to be a negative z-score if the data value is below the mean. So that's important to keep in mind. The formulas for calculating the z-score are given here. They both have this is your data value, the x, and then this is the mean. If you remember that the mean for a sample is x bar, but the mean for a population is mu. So in either of these, basically what we have is we have our data value minus the mean, and then we're going to divide that by our standard deviation. Okay, it's just these have different symbols depending on whether we're talking about a sample or whether we're talking about a population. Okay, we have a rule for rounding, and that rule is that we always round to 2 decimal places. So that's really important that you remember z-scores are rounded to 2 decimal places. There are 2 places later in the semester that we'll get to that round to 3 decimal places, and I'll tell you what those special ones are, but all others will be to 2 decimal places. Okay, a few properties of z-scores. First of all, like we said, the definition of a z-score, it's the number of standard deviations that a given value x is either above or below the mean. So if you have some number and you want to know how many standard deviations it is above or below the mean, then that's going to be indicated by your z-score. They have no units, it's simply a number, and we can use that for comparison purposes. So we take something that might be inches or it might be pounds, and you convert it to the standard score, and then you can compare it regardless of those units of measure. The third bullet here that we want to talk about is a data value is significantly low if its z-score is less than or equal to -2, and is significantly high if the z-score is greater than or equal to +2. That goes back to the range rule of thumb, which says that basically it's significantly high if it's more than 2 standard deviations above the mean, and is significantly low if it's less than 2 standard deviations below the mean. So that's kind of the same idea, except instead of having to figure in the standard deviation, because it's already been standardized, you just use the number -2 or the number +2. And then if an individual data value is less than the mean, then the z-score is going to be a negative number. Okay, so here's an example. Which of the following 2 data values is more extreme relative to the data set from which it came? And by extreme, we just mean like either further from the mean is basically what more extreme means. So in this first one, you've got a 4,000 gram weight of a newborn baby, and we want to compare that to the 99 degrees Fahrenheit temperature. So we're comparing grams to Fahrenheit. Certainly this is apples to oranges. We've got to find a way to equate the two. And so we're given this other information here. So it says among 400 weights with a sample mean given and a sample standard deviation. So we're going to take this this baby that weighs 4,000 grams, and we want to see how it compares to basically the mean, or the here that's given for the babies. Same thing with the temperature for the adults. So on the first one, we're going to use our formula. Because it's talking about a sample, we're going to use x minus x bar divided by s. So talking about the baby, this individual weight here is going to represent our x, and we're given our x bar. and we're given our S. So we're going to plug all of these in. So we'll have 4,000 minus 3,152. We're going to divide that by 693.4. So a couple things to remember. One, I would put this in parentheses when I'm putting it in the calculator so that you get an accurate calculation. The other is that the data value always comes before the mean. I see a lot of people mix these up, and what will happen is your number will be right, but the sign will be wrong. So if you're consistently seeing that that's your problem, you need to recheck how you're entering these values here. Okay, so when we do this one, we get 1.22. So remember, round it to 2 decimal places, and also there's no units associated with that. So this z-score is 1.22. When we go to do the next one for the temperature, we're going to be using the same formula here. And in this case, we have a temperature of 99. That's going to represent my x. So this will be 99 minus the mean. So here's my mean. So 98.20, and I'm going to divide that by the standard deviation. Okay, again, put parentheses around the numerator. So we end up with a z-score of 1.29. Okay, so now we can compare our z-scores to know which one is more extreme. So the baby had a z-score of 1.22. So that was 1.22 standard deviations above the mean for newborn babies. So this one is 1.29 standard deviations above the mean temperature for adults. So this one is further above the mean than this one, and therefore this is the more extreme value, the 1.29. So convert to a z-score. It's a fairly simple conversion, so convert to a z-score and then compare those to see which one is more extreme. So here's a few slides if you want to look through them and just kind of compare what we did. These are available on the PowerPoint that you're welcome to pull up. Okay, so using z-scores to identify significant values. Before, when we were determining if something was significantly high or significantly low, we would do the mean plus 2 standard deviations, and we do the mean minus 2 standard deviations. But because we've already standardized these to z-scores, we just have to look at the z-score itself. So if I have a z-score that's larger than 2, then it's going to be considered significantly high. If I have a z-score that's less than -2, then it's going to be considered significantly low. Anything between -2 and 2 is not going to be significant. So you want to keep that in mind. Those two that we just looked at, we had x is 1.22, and then we had another one, sorry, not x, z. Z would be 1.22, and then Z would be 1.29 for those two examples we just did. Both of these fall in this category here where they would not be considered significant, either significantly high or significantly low. If you had a z-score of 2.5, then that would be significantly high. A z-score of -3.1 would be significantly low, and so forth. Okay, here's an example. Is the platelet count of 75 significantly low? So the lowest platelet count in a data set is 75. Okay, so this is the data value. This is my X that I'm wanting to work with. Is that value significantly low? Assume that platelet counts have a mean. So here's the mean that I'm going to need and a standard deviation here. Okay, so Z is going to be X minus X bar divided by S. So it would be 75 minus 239.4 divided by 64.2. So when I look at that conversion, I get -2.56. So a couple things to mention here. The data value that I'm working with is clearly below the mean, so I would have expected a negative z-score. When I look at this, it's below -2, so therefore it would be significantly low because of this. Okay, here's an example for finding z-scores that I would like for you to pause the video and practice with. Okay, these are the z-scores that you should have gotten when you did the calculation. One thing I want to mention is we would actually on this problem be using the population formula for calculating a z-score, which is x minus mu divided by sigma. The reason for this is that we're not referring to a sample in this. It says assume the mean weight of 16-year-old females. So we're basically thinking that this is all 16-year-old females. And so that mean weight would be the 118. So that's going to be my mean of the population, which is mu. And this is going to be my population standard deviation, which is sigma. So when I go to plug these in, it's still the data value, which are these values given here. These are the x's. Okay, so it's going to be the x minus the mean divided by the standard deviation. Remember to put your parentheses around the numerator. And when we look at these, the only one that is significantly high is going to be this 2.7. And this is actually on the borderline of being significantly low with that. So the B and D are below the mean and they end up with a negative z-score. And A and C are above the mean and they end up with a positive z-score. There's always some question about is -2 considered significantly low because it's right on the cutoff. And if it is -2 or lower or +2 or higher, those are the ones that are significant. It's the ones in between that that's not significant. Okay, a lot of times you have questions on your homework about which one is better, a high or a low z-score, and there's no one answer for that. It all depends on the context of the problem. So if the problem is comparing like SAT versus ACT scores, then it would be better to have a higher score is going to be better in those cases because you want to achieve a higher SAT score or a higher ACT score. So you would want a higher z-score to be the better one relative to the two. Cholesterol is a case where a lower score would be better. So a lower z-score would be better in terms of knowing which one was a better relative score, your LDL or your HDL. A golf score, it's better to have a lower score. Grades, like if a statistics classes grade versus some other classes grade, then grades are better to be higher. So it's all relative as far as comparing the z-scores. It's relative to what you're measuring. Okay, as far as which is more extreme just means further from the mean. So if you have your mean here and you have a value here and you have a value here, then this one's going to be your more extreme value because it's further from the mean. Extreme doesn't necessarily mean in a particular direction, either high or low. It just means further from the mean. Okay, moving on to percentiles. Percentiles are measures of location. They're denoted with these capital P's with the little subscript. So this will be my first percentile, second percentile, up to the 99th percentile because you take all 100% and you divide it up 100 times, and I'm not going to put all those in there, but you get 100 little divisions in there, so you end up with the 99th percentile, and each one of those represents 1% on this on the spectrum that we're looking at. So an example of that would be the growth charts that you have in as a child, like at the doc. Okay, so this is an example here of a growth chart that you see at the doctor's office, and you can see that depending on the age, this one is for young boys between birth and 36 months. So looking at this, you can follow these lines and it's going to tell you if you're in the 5th percentile for your weight, the 10th percentile, the 25th, the 50th, 75th, 90th, and so forth. These percentile charts are definitely one way that you can use percentiles. Standardized tests are another way that percentiles are used, like when you are given your score, you're not given a raw score necessarily on some type of standardized test. Maybe you took the end of grade test here in North Carolina or end of course test and they told you that you're in the 85th percentile. That means you did better than 85% of the people that took the test. If they had given you a raw score and said your raw score was 428, you wouldn't really know what that means as far as how you compare to other people that took the test. That's why the percentile gives you a measure of relative standing. You find out how you performed relative to other people, and that's why percentiles are these measures of relative standing. So standardized tests and growth charts both give you an idea of how you compare to other people. Okay, so we want to look at being able to convert back and forth between a percentile and a data value. So the first one we want to look at here, we're going to go through the process of finding the percentile that corresponds to a particular data value X. Okay, so with this, what we're going to do is we're going to have to find, and literally we're going to count for this. If we look at our setup here, our formula, to find the percentile of a particular value X, we need to look at the number of values that's less than X divided by the total number of values in the data set, and then multiply that by 100. Okay, so if we look at this example here, we want to find the percentile for the data speed of 11.8, and this is for Verizon cell phone data speeds. So this chart needs to be in order. So if it's not in order, then you need to put it in your calculator and sort it so that it is in order before you start working with it. So they have to be in order. So if we look at what our directions said, if we want to find the percentile value of the 11.8, we need to find the number of values that's less than 11.8. So looking at 11.8, 11.8 is here. So we want to count how many values we have. So that's 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 in each row. So that's going to be 20 values that are less than the 11.8. Okay, going back, we want to divide that by the total number of values in the chart. So each row we said had 10, so that's a total of 50. So we're going to do 20 divided by 50. And then finally, we're going to multiply it by 100. And our rounding directions are round the result to the nearest whole number. So here, I'm going to multiply this by 100. And that's going to give me 40. So this is going to represent the 40th percentile. Okay, so this is just kind of going through some more steps here. And that basically, if it's the 40th percentile, then that means there's 40% below that value and 60% above the value. Okay, if we look at this example here, on this one, we want to find the 16th, or not the 16th percentile. We want to find the percentile for the value 16. So if I go down and look for the value 16, here's the value 16. So I need to know how many values there are less than that, not including it, but less than that. So that's going to be 10, 20, 30, 31, 32. So there's 32 values less than 16, and that's out of a total of 50. Remember, 50 is the number of data values. It's not always going to be 50. That's just relative to this particular example. We'll multiply that by 100. And we're going to find that that equals 64. So this is the 64th percentile. So 16 represents the 64th percentile. There's 64% of the values below that and 36% of the values above. And I will say there are multiple ways to find percentiles and eventually quartiles that we'll talk about in a few minutes. So if you happen to see them done a different way, it doesn't mean one way is right and one way is wrong. There's some controversy with how percentiles are calculated, but this is how I want you to calculate them for our purposes. Okay, so that's kind of going from a value to the percentile. So now we want to turn around and go from the percentile to the value. In order to do that, we need to make sure we're clear on our notation. N is always our sample size, or the total number of values in the data set. K is going to represent the percentile that we're using in the problem. L is simply a locator value that we'll talk about. And then this piece of kth is going to represent the kth percentile. Okay, here's a little flow chart that you're welcome to go through, but I'm just going to work through some examples and I think you'll understand how it works as we go. Okay, on this one, we want to find the 40th percentile, and that's going to be denoted by the piece of 40. So the first thing that we want to do is we want to take that 40, and it's like we're undoing the process that we just did. So the process that we just did ended by multiplying by 100. So this way we're going to start out by dividing by 100. And again, this is converting a percentile to a data value. So we'll do 40 divided by 100, and then we're going to multiply that by the number of data values. So we had 50 data values. So to kind of summarize this, we've got the percentile. We're going to divide that by 100, and we're going to multiply that by our sample size, or our n. So when we do that, we get 20 here. And this is where it's a little bit confusing, because we have what we're going to call case 1. Okay, and with case 1, if we end up with no decimal for our L. Okay, so this is our L. I didn't say that, but this is our L. If we end up with no decimal, so this is just 20 with no decimal out here. So what we have to do is we have to average that data value with the next data value. Okay, so if we look at this, what I've got to do, we said originally L was a locator value. So I've got to find the 20th data value, and I've got to find the 21st data value, and I've got to average those two together. So again, make sure that this is in order. It's still the same data set, so it is in order. So we want to go to our 20th data value. So there's 10, and then 20 is going to put us here at 11.6. So this is going to be 11.6. And the 21st value is 11.8. So we want to then average those two together. So we're going to get 11.7. And that's going to be our answer. So there's a lot of things kind of going on here. One, a lot of people will do this calculation and say that 20 is your answer. 20 just gets you started, okay? It tells you where to go in the chart. So you want to go, again, since there's no remainder here or no decimal, then you want to take the 20th and the next one, which will be the 21st, add those together and divide by 2, and we'll get 11.7. If you're a little bit confused at this point, just kind of bear with me, because we're going to look at several examples here. Okay, this one we want to find the 75th. Okay, the 75th is actually going to demonstrate case 2. So case 2, we have, so L has a decimal, or has a remainder. Okay, so with this one, we're going to take percentile. We're going to divide it by 100, and then we're going to multiply it by n. So my percentile was 75. I'll divide it by 100, and then I'm going to multiply it by 50. Okay, when I do that, I'm going to get 37.5. So that's my L here, is 37.5. Okay, so that means that I'm going to use the 37.5th value, except what I have to do is I actually have to round this up. And so I'm going to look at the 38th value. So on this one, we round up and then take that value. Okay, so we'll go to the 38th value, and that's going to be our answer. So we've got 10, 20, 30, 1, 2, 3, 4, 5, 6, 7, 8. So that takes us here to 21.5. So 21.5 is the 38th value, and that represents this P sub 75. I have our calculator value, the locator value was right in here, kind of halfway between the 37th value and the 38th value. If I went down to the 37th value, then I don't have 75% below that, which is what I need to have. So that's why I need to actually go up to this next value, which is the 21.5. Okay, here's a couple other examples. If you feel comfortable and want to try these on your own, go ahead. If not, then just keep listening. I'm going to go through this. So again, we're going to take the percentile, which is the 65. We're going to divide that by 100, and then we're going to multiply that by the number of data values. So when I make this calculation, that comes up to being 32.5. So I have a decimal here, so that tells me that I'm going to round it up to 33. So I'm going to take the 33rd value. So the 33rd value is going to be 16.0. So my answer for this one would be 16.0. All right, last example. If I want to find the 30th percentile, I'm going to do 30 divided by 100, multiply it by the number of data values, which is 50. And when I do that calculation, I end up with 35. Actually 35 is not what I end up with. I end up with 15. Okay, so I don't have any decimal part to this. So this is one of those where I have to take the 15th and the 16th and average them together. So my 15th value, there's 10, 11, 12, 13, 14, 15. So here's my 15th value, which is 10.2, and my 16th value, which is 10.3. Divide that in half, and I get 10.25. So that would represent my 30th percentile. Okay, moving on to quartiles. With quartiles, basically what we've got is we've still got this whole, we've got the 100%, but we're going to divide it this time into 4 parts. So we've got this middle, which is our second quartile. Halfway between that is our first quartile. Halfway between the second quartile and the end is the third quartile. So when we look at this, we've got, this is also called the median. So when you are looking on your calculator at one variable stats, you're not going to see this second quartile. You're only going to see median, but those are one and the same. So the one variable stats menu will give you your quartile values. And so looking at that, you can get these from that. And it divides it into 25% segments. So we've got 25% in each one of these to divide that up. Okay, so the first quartile is the same as the 25th percentile, and it divides the bottom 25% and from the top 75. And you can kind of see that here. You've got the 25 and the 75. The second quartile is the same as the median. It separates the bottom 50% from the top 50%. And the third quartile is the same as the 75th percentile, and it separates the bottom 75% from the top 25%. Okay, so looking at one reason we want to find our quartiles and our percentiles is to be able to find these different ranges, which can help us determine outliers and so forth. The main one that we're going to work with is the interquartile range, which is referred to as the IQR. With that, you have to subtract the third quartile minus the first quartile. If you want to get your semi-interquartile range, then you do the interquartile range divided by 2. The mid-quartile range, you add the third and first quartiles and divide by 2. And then here with your 10-90 quartile range, you're going to subtract those percentiles. So again, we're not really going to use these bottom 3, but the top one we will use for identifying some outliers. Okay, the 5-number summary is also important, and it's important because you'll use this in graphing your box plots and so forth. So with the 5-number summary, there are 5 numbers that you have to use in doing the 5-number summary. The first one is the minimum value. The second is your first quartile value. The third is the second quartile value, which is the same as your median. The third value is the fourth value is the third quartile, and then the fifth value is your maximum. So you need to be able to identify your 5-number summary values. Okay, so if we want to look at this data set here and find the 5-number summary, so we just said our 5-number summary is the minimum, the first quartile, the median, the third quartile, and the maximum. Okay, so these again need to be in order. So we can pretty clearly see the minimum is going to be 0.8. The maximum is 77.8. Okay, the median we know is the middle two values because this is a data set of 50. So we need to find the average of our middle two values. So we've got 20, 21, 22, 23, 24, 25. So here's our middle two values. So if we average those two together, 13.7 and 14.1, then we're going to end up with 13.9 for our median. Okay, so our median is here in the middle. The first quartile is the same thing as the 25th percentile. You could go through the process that we just did for finding the 25th percentile, or another way to look at that is to actually look and find the middle half of the lower half. Okay, so if I've got half of my data is divided here, then if I find the middle data value of this bottom half of my data, that's going to represent the first quartile. So looking at the bottom half of the data, that's 25 values. So if I go to the middle of the 25 values, that's going to be my 13th value. So that's going to be this 7.9 because that's my 13th value. Okay, to find the third quartile, I'm going to do the same thing. I've got 25 values that are larger than the median here. So here's my median. So I want to find the 13th value there. So that's 5, 10, 11, 12, 13. So this is going to be the middle value on this. So that's going to be 21.5. So these are my 5 number summary, the 5 numbers that are part of the 5 number summary that I need. Okay, you should be able to graph what's called a box and whiskers graph or a box plot. And it's a graph that basically consists of a line extending from the minimum value to the maximum value. And on that line, we have lines drawn at each of the quartiles, the first quartile, the median, and the third quartile. Okay, so if we look at this example here, I like to personally scale this a little bit so that it comes out looking pretty nice. If we look at doing this, our values go up to 77.8. So I'm going to just do this by tens. So 10, 20, 30, 40, 50. We don't really need to scale the vertical axis here. There's no real reason for doing that. So I'm going to go and I'm going to put a vertical line at 0.8. So I'm just going to have to kind of estimate that. Put a vertical line at 7.9. Put one at 13.9. Put one at 21.5. And then finally over here at 77.8. Okay, so I'm going to go in and I'm going to connect the first quartile and the third quartile together and form a box, hence the name box plot. And then I'm going to draw a straight line out and connect the minimum and the maximum. So what this tells me is that our data is kind of heavily skewed to the left, and or we've got more data to the left, so it's actually skewed to the right because this is where our tail of the graph would be. So in looking at that, we have a tail that's kind of tailing off to the right, so it would be right skewed if we were to look at the graph. But we can see the concentration of our data here more to the left. And you can see a little bit better diagram here of that. If you don't scale it, you lose kind of the value of the box plot because you're not able to see that it's concentrated on the left side. And we just talked about the skewedness of the graph. Okay, so I want to, in order to do what's called a modified box plot, you actually have to identify what your outliers are. And this is where that interquartile range comes in, or your IQR. So we want to be able to figure out what the IQR is for this. Once you have your IQR, you're going to multiply it by 1.5 and then either add that to the third quartile or subtract it from the first quartile, and anything outside of that will become an outlier. So if we look at our values here, we found that our third quartile was 21.5 and our first quartile was 7.9. So if I subtract those two, I get 13.6. So what I want to do from that is my first quartile, like I said, was 7.9, and my third quartile was 21.5, and my IQR is 13.6. So I want to take that 13.6 and multiply 1.5 times the IQR. So I'll have 1.5 times 13.6, and that's going to give me 20.4. Okay, this value is important because what I'm going to do is I'm going to take the third quartile and add that 20.4 to it. So I'm going to have 21.5 plus 20.4, and that's going to give me 41.9. Anything larger than 41.9 in our data set is going to be considered an outlier. I'm going to go and look on the bottom side by doing the first quartile minus that same 20.4. So that's going to be 7.9 minus 20.4, and that's going to give me negative 12.5. So anything lower than negative 12.5 is going to be considered an outlier. So we want to look at our data set and see which ones, see if we have any that's larger than 41.9 or smaller than negative 12.5. So when we look at this, 0.8 is our smallest value, so we don't have any outliers on the lower side, but we had calculated that to be 41.9. So we have four values that are larger than 41.9. So all four of these would be considered outliers based on the formula for calculating an outlier. So when we go to construct a modified box plot, basically we're going to put some kind of asterisk to identify where those outliers are. And we're going to mostly do these with the calculator and StatCrunch. So I want to take a minute to hop over to both the calculator and StatCrunch to show you quickly how you do these on the calculator and StatCrunch. Okay, so here I am on the calculator. So the first thing you would want to do is to go to Stat, Edit, and make sure that you have your data values entered. I've already taken the time to enter those. If you want to pause and enter the data values from the data set that we've been using, then that will be fine. From here, you want to go to Stat and Y equals, which brings up your stat plot. We want to choose the first one. On this one, you want to make sure that on is highlighted. And then I think for a lot of us, we had it last on the histogram. So you want to come down where it says type and go all the way over to, for now, we're going to choose the fifth graph and press enter to make sure your calculator has accepted that. Make sure your X list is correct. And then instead of pressing graph, which is our tendency to do, we want to always do zoom and number 9 for zoom stat. And here is that same box plot that we just got through doing. If you press trace and use your arrow keys, then you can go back and forth, and it'll actually down here at the bottom show you that our minimum value is 0.8, our first quartile 7.9, our second quartile, which is our median, is 13.9, third quartile is 21.5, and then our maximum is 77.8. If I go back to my stat plot and choose the fourth graph is actually the modified box plot. So I'm going to do zoom 9 again. And this time you can see those four that we identified through our calculations that we said were outliers. You can see those. If you use the arrow key, actually do trace and then the arrow key, you can go over and it'll take you to each outlier and tell you what the values are that correspond with those outliers. So that is how you do the box plot and the modified box plot on your calculator. So over on MyStatLab, if you go to your StatCrunch, open StatCrunch. Okay, here I've pulled up a sample of data that I want us to take a look at graphing the box plot using StatCrunch. If you go to graph and then over to box plot, and then I want us to actually choose both of these. So if you do control and then click each one of these, that's going to allow us to graph those. And I'm going to actually, I like mine drawn horizontally. You don't have to do that, but I prefer that. And then I want to mark the mean and the median on our graph just so we can see that. And if you press compute, then here we have the graphs. And so you can see the outliers are marked with the dots here. And you can also see your quartiles and your medians and your interquartile range, your lower limits, your upper, and so forth when you highlight that. And it's good for comparison purposes. Box plots are really good about comparing these. So you can see that in general, the male pulse rates were a little bit closer together, had less spread of the data, and on the female pulse rates, they were a little bit higher. So you can also see that as well. So it shows a lot of good characteristics there. Okay, that takes us to the end of chapter 3, and that's also the end of our first unit. So we'll be stopping and reviewing in the next class and then getting ready for our upcoming test. So join us for any Zoom sessions on Wednesdays, and be sure you're keeping up with all quizzes and tests as needed, quizzes and homework as needed in my stat lab. And contact me if you have any questions or join the SI sessions as needed. Thank you and have a good day.